So welcome everyone. Welcome to the first colloquium in this semester. George, as the new department head, had vowed to bring back the series, restore funding, and obviously was successful. So there's also a new committee, and we hope that we can continue the good work that Helmut has done, that it's as intellectually stimulating and exciting as it has been in the past. Okay, so today we start with our very own John Hardy. We're very happy that he agreed to give a talk, and he actually will talk about an important topic in the history of science, Ernest Rutherford. So let me say a few words about John. And I pulled this off the internet because somehow I couldn't find you in the office. So it must be true, right? So you graduated from McGill in 1965. Got a PhD there, right? I didn't say that. What was that? Okay, and then he worked up the ranks, and he ended up being divisional director in Chalk River, which is a national lab in Canada for nuclear science. And then in 1997, he came to Texas A&M and has been here ever since, and he's a distinguished professor. And among his many awards, I just mentioned Rutherford Medal of the Royal Society of Canada in 1981, and the Warner Prize, which is the highest honor in nuclear physics that the APS gives away in 2006, I believe. And he's usually more into fundamental interactions and precision measurements about fundamental actions in the standard model. But today, it's all about Ernest Rutherford. So, yeah, welcome, John.
Thanks. I don't think I've ever been applauded by my colleagues before. That's nice. Let me try and get this on. Okay, does that give enough sound? All right. So, as Rainer said, I'm an active nuclear physicist and doing experimental nuclear physics. I'm not a historian, so I think maybe it's worth at least starting by explaining how come I'm talking about history. It all began about a year ago last November when I got a phone call from the people who headed the nuclear physics division of the Canadian Association of Physicists. And they invited me to give a talk during the centennial year, so that was to be June of last year, at the annual general meeting of the Canadian Association of Physicists. So 8 months away at the time, I thought, well, okay, that'll be fun. Sure, why not? Well, needless to say, 6 months later, when the date was approaching and I was realizing that I knew practically nothing about Rutherford, that caused me considerable effort. And worse than just having to prepare a talk, I didn't know how long any given slide would take me. I mean, we all know in physics, if we give enough talks, I can riff on a slide with an equation on it for X minutes, so I know I need Y number of slides to take me through a lecture. Well, I didn't know with history, I don't know that much to kind of ream off some variations on a theme. So I prepared a number of slides that I thought would for sure take me through the half hour that my invited talk was. Well, needless to say, I got about halfway through when the time was up, and I managed to end it in a sort of reasonably coherent manner. But there was half this talk that I'd prepared and I'd never given. So here I am. I have the opportunity to give you an hour's worth, so here it is. Now, I mean, I might also say that, why was I invited to give such a talk by the Canadian Association of Physicists? And I mean, it may well be that the young guys who were organizing the meeting thought I was perhaps old enough to have known Ernest in his heyday. I did not. However, when you were told that I had got my PhD in '65, and there was some nasty remark back here. In fact, I took my first nuclear physics course in 1961, which more or less bisects the century between now and when Rutherford first realized that there was a nucleus. Not only that, but my first course in radioactivity, there were two courses, one was just nuclear physics, the other was radioactivity, was given by a rather elderly gentleman who had been a student of Rutherford's And not only that, this course was given in the same building that Rutherford did his Nobel Prize-winning experiments in when he was a professor at McGill. So I have some legitimate connections, albeit one generation removed, to the man. That didn't mean I knew much about him, beyond the fact that he'd been at McGill. So what I'm going to talk about is sort of 4 sections, his life. So first of all, some just sort of where he lived, where he moved, what he did over his life. Then some real science, albeit 100-year-old science, but I think you'll be amazed, as I was, at the ingenuity of these guys. I mean, these people worked with so much less than we have, and they were smart, and they had not only lots of brains, but they had intuition that is staggering. You know, the things they deduced or induced their way to, I suppose, is amazing. Then something about his research style, and so much of what we do in nuclear physics today, and in particle physics, for sure, same thing, started with Rutherford. I mean, we're doing the same things he was doing 100 years ago in many ways, with far better techniques, but we're doing the same stuff. But we're doing it very differently. The number of people involved, the complexity of the equipment, and so on. So it's kind of interesting to make that comparison. And then finally, what's the influence? How are we influenced today? And again, I think you'd be amazed. So first of all, his life's path. He was born to a farmer. He was the 4th child of 12 in frontier country. I mean, New Zealand was settled a lot more recently than the United States. Think the western U.S., except without the Wild West. I mean, I don't think there were any gunfights at the OK Corral in New Zealand, but this was rough country, far from the civilized world. So his family didn't have much wherewithal to put him through school beyond just the local country schoolhouse. Well, fortunately, in addition to being kind of a strong farm boy, you know, so he was generally good in sports and so on, but he was also reasonably smart, managed to get scholarships, ended up getting his university education at something called Canterbury College in Christchurch, New Zealand, South Island of New Zealand. And this was a college of the University of New Zealand. But the University of New Zealand, the only university in New Zealand at the time, had only been formed 10 or 20 years earlier. So the Canterbury College, you see a picture of it, and it's smaller than our physics building, the whole place. So, you know, this is fairly primitive stuff. He managed in the course of, well, he went there in 1891. He spent 4 years there, managed to get a MSc, an MA, a BSc, and a BA in 4 years. Now, it's not, I think, because he was a genius. It was probably because, you know, there weren't a lot of courses to choose from, and you went through like that. He had to do some research as part of his last degree. His BSc was the last, actually, in that list. And what he did was work developing what turned out to be a radio receiver. And in fact, when he went to Cambridge, which he did, I'll say in a moment, he had the world's record for sending and receiving radio waves of about 2 miles before Marconi had even made his first patent. So had he stayed in that area of research, he might well have been as renowned as he is anyway, but for a different reason, in a different field. Okay, so he then applied, after he'd finished his work, his college degree in New Zealand. He didn't really want to be a school teacher, which was about the only option he had. And he certainly didn't want to work on his father's farm. So he applied for something called an 1851 exhibition scholarship. This was in 1851 in London, the first World's Fair was ever held. And it was probably the last World's Fair that actually made a profit. So when they made that profit, they assembled the money and turned it into a scholarship fund, which still goes to this day. And it was for, principally for young people in the Empire, or in the colonies, or whatever you want to call it. And New Zealand's turn came in 1891. He applied and he lost. It went to a chemist. However, the chemist had a fiancée and a job and decided to stay in New Zealand, Rutherford, who had a fiancée, had other priorities, as probably many physicists have had in more recent times, and decided to leave his fiancée back in New Zealand, and in fact didn't come back for 5 years when he came back and met this poor woman who'd been waiting all that time. So he left for Cambridge University. There's New Zealand, there's Cambridge. It's a bit of a pain to fly it these days. It would probably take 15 hours or something like that. In those days, it took 6 weeks by boat. So if you imagine, this is really quite an extraordinary move for the time. We think now you can be born anywhere and you can become a world-famous physicist or any other thing you want. In those days, if you're fourth child of 12 in a remote frontier country, thousands of miles away from the center of the world, which was here. I mean, science happened here, not here, I'm afraid. So it was centered around England and Europe. So he was moving from a remote place. Furthermore, Cambridge, being Cambridge, had, until this time, it only allowed its own graduates into its graduate school. So you had to have a bachelor's training from Cambridge in order to take graduate work at Cambridge. Obviously, because Cambridge is so much the center of the earth that mere colonials shouldn't really be allowed to muck in with you. Well, the fact is that he was there the very first year. So, I mean, you think of all these coincidences that, you know, he didn't get the scholarship but did because somebody dropped out. He came to England, and just the first year when colonials or non-Cambridge graduates could take graduate work there, initially that meant he was treated like a boorish outsider, but he managed to overcome that by showing that he was pretty smart. So first year for foreign students, and he worked with J.J. Thomson. Most of you have either lectured about him or been lectured about Thomson. He was the one who did the E over M experiment on the electron. Then when he got his, I don't think they got a degree. I don't think he really got a PhD. But when he completed his graduate work with Thomson, there was an opening at McGill University. And I was pretty remote too, although not quite as remote as here. I mean, that's in Montreal. And it was professorship, full professorship. He's 25 years old, 26 years old. And so Thomson, though, had a pretty good reputation. And so he was very keen on Rutherford at that point, having seen how smart he was. So he recommended him for the position. And graduate students soon to look for a job might be amused to know that McGill sent the head of the department and the principal of the university over to England. So that's a 1 week boat trip both ways in order to interview him. Imagine you're applying for a job and the president of the university and the head of the department comes to you. Times have changed. But he got the job, and on his way he wrote his fiancée the following message: I am expected to do a lot of original work and to form a research school in order to knock the shine out of the Yankees. When I gave this in Canada, I added to it, Canadian attitudes haven't changed much in 100 years, and I got an even bigger laugh. So, at any rate, that was his job, or as he saw it. He then stayed there for 9 years, did all the work for the Nobel Prize, for what he got the Nobel Prize for, but was attracted back to England, to Manchester, where he arrived early in 1908 and got awarded the Nobel Prize a few months later. So the Nobel Prize was for work done at McGill, but was given when he was at Manchester. And then at Manchester, of course, he was there for 10 years or more. Oh, but when he got to Manchester, he wrote this to a friend, an American friend actually, or at least somebody who worked in the States. I find the students here regard a full professor as God Almighty. It's quite refreshing after the critical attitude of Canadian students. Something else that I'm sure American students fall in the same category. Not, that is, treating professor like God Almighty. I've never seen any example of that. So after being in Manchester through the First World War, he then went to Cambridge as the Cavendish professor. That means he replaced Thomson. J.J. Thomson, and then stayed there until his death in 1937. Just as a matter of interest, I mean, the first Cavendish professor was Maxwell, Clerk Maxwell. So, you know, this is not an undistinguished position, to put it mildly. Now, just as an interesting overview, some of his students and what I call acolytes. So this, what I mean there is postdocs, younger colleagues who worked with him at some period, and these are the ones that you would have heard of or would be impressed at least by the Nobel Prizes. I mean, how many among us could say, no matter what our age, that we have worked with or mentored or whatever, that many people who got Nobel Prizes? So we have Soddy, who he worked with at McGill, got the prize in 21 for the origin and nature of isotopes. Otto Hahn for fission. Soddy was a faculty member at McGill. Otto Hahn was a postdoc with Rutherford at McGill. At Manchester, Niels Bohr was a postdoc. Von Hevesy, von Hevesy is a Nobel Prize. Henry Moseley, most of you know, used X-rays to determine the elements and would certainly have been a Nobel Prize winner if he hadn't been mowed down in the trenches in World War I. Hans Geiger, we've all heard of the Geiger Counter. He was Rutherford's assistant, and in fact, together they developed the Geiger Counter, so it could as easily be called the Geiger-Rutherford Counter. Then at Cambridge, Chadwick for the neutron, Blackett, cloud chamber, Cockcroft and Walton for transmutation of nuclei. We think of them as accelerator builders. And Kapitsa, who was for low temperature physics. That's probably not a complete list. Rutherford himself got the prize in 1908 for the disintegration of the elements and the chemistry of radioactive substances. It was actually a chemistry Nobel Prize, which is odd and is politically related, and it's a long story I won't go into. Just to show that he was a reasonable human being, that's the car, that's him and his wife in the car that he bought with the Nobel Prize money. So, no doubt he stocked his lab and did other good things, but he didn't neglect to buy himself a car. Okay, let's do something about science, since that's why most people are presumably interested in Rutherford. So, I think what is startling about this is how much Rutherford actually discovered that we take for granted and we don't associate Rutherford's name with it. First of all, while he was still at Cambridge, he was looking at the radiation given off by uranium, and he discovered that there were two different, at that time, I think he only recognized there were two different types of radiation, which we now know as, this is depending on their range. Some of it was short range, some of it was longer range. He called them alpha and beta, for the lack of any other name. He was the one who first observed the difference. He was the one who named them. So whenever we say we have an alpha or a beta, thanks to Rutherford for that. And at McGill, he then, since he didn't have, at the time, a source of uranium, but he did have a source of thorium, radioactive, naturally occurring. These are all naturally occurring, right? Nobody could make any of this stuff. You just had to deal with what you could get. Marie Curie, of course, separated out radium, so that was her thing, was to look at the decay of radium. For Rutherford, initially at least, it was thorium. So it had the same two radiations, so it had alpha and beta radiation, but it had something really puzzling. It looked as though the radioactivity was moving around. That is, it would start off here, but then they'd find it out here on the walls of a chamber. So what was going on? And I have to now give you this plot, which I know some of you can't see other than the outline. This is one of the radioactive chains. So this is the thorium decay. You start with thorium here, which has 1.4 times 10 to the 10 years. Then when you have a line like that, that's emitting an alpha particle. This is what we know today, right? This is not, Rutherford didn't have this map in his back pocket. When it moves in this direction, it's a beta decay. That's an alpha, 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 and so on. This is the names that we apply to them today. So this is thorium, this is actinium, this is radium, this is radon, and so on. And that's the mass number. So it's thorium-232 is what he started from. But of course, what you have to realize is they barely knew, and they didn't know, the entire periodic table. For example, argon and helium had only just been discovered about 5 years before this. Furthermore, they thought that each element, so each thing down here, that each element was separated from each other by unit masses, perhaps one, perhaps two masses, but the mass of hydrogen. So not ridiculously out, but remember they had no concept of isotopes. Every element, every atom was unique for each element, and their masses would be separated by probably a hydrogen. That was the thinking. So there was no idea when you see from thorium that you see stuff coming off. You have no concept that it's rattling down like this. You just have thorium, and it's doing something. So what's it doing? So what was moving around? I mean, they, needless to say, had great problems trying to figure out what was moving around. So, but Soddy, who was a chemist, managed to, well, first of all, they both together, Rutherford and Soddy, called it emanation. So this, where are we? Here, emanation. Sometimes called thoron, and as you see, it's a radon isotope. So we all know from basements of houses having this, that radon moves around as a gas. And they also determined that it behaved chemically like an inert gas. This is in 1898, which is 4 years after the first rare gas had ever been seen. So, I mean, they're on the forefront, just lucky enough to be there after and not before inert gases were first observed. Then they managed to separate out something. It was thorium X, which is radium, but they didn't know that. They just knew Soddy played around with the chemistry, and he found he could extract something which he called thorium X, because he thought it was still thorium, and observed that all of the radioactivity went with it. And what was left behind was inactive. Already kind of interesting. But then he found that what was separated, the thorium X sample, decayed in time exponentially, although that he just knew it decayed, right? And that what was left behind grew exponentially, because that just means the thorium X that you've removed from here is rebuilt from the decays of the thorium above it. So that's from his paper. That's what he observed. And in case you didn't know, he was the guy who wrote down for the first time the exponential decay and the exponential growth, which he derives from the usual probability methods, and showed that it fitted the data. So whenever you look at a radioactive decay, Rutherford's the first who saw it and identified it and recognized it. So at this time, as I've said, every element had a unique atomic mass. By the way, there's one of the big puzzles of the time was the fact that they certainly figured that the order of the elements went from argon to potassium to calcium. But if you've never noticed, the argon is heavier, that is naturally occurring argon, is heavier than potassium. So they're out of order. The order of the elements goes one way, the order of the masses goes a different way. And if you don't know what isotopes are, you're really stuck. And so they kept thinking people had made mistakes in the measurements of the masses and so on and so forth. So to give you a measure of their ignorance at the time. So they believed that every element had a unique atomic mass, each one by a different integral multiple of the hydrogen mass. By then, courtesy of J.J. Thomson, everybody knew that the electron, the beta particle, but they quickly identified betas with electrons. The beta particle was known to have a mass far smaller than hydrogen, so there was no, how could you change from one element to another if you were just releasing a particle so much lighter than hydrogen, right? Because if every element is separated, has only one isotope, you don't know what isotopes are, and is separated by the mass of a hydrogen, how can you get from one to the other with the mass of an electron disappearing? So Rutherford quickly, by his intuition, realized that the alpha particle was the real question. What was the alpha particle doing? And at the time, it wasn't even clear that the alpha particle was a particle. It was radiation, and it had been put in magnetic fields and not seen to deflect. The electron, of course, is really light and deflects in the sort of magnetic fields that they had at the time. The alpha particle is massive and energetic, coming out of these radioactive decays, so it didn't bend. So what was going on? What was the alpha particle? So, devised an ingenious experiment which actually depended on Marie Curie's generosity in sending him a pile of radium. And I mean, we can only guess today what the activity of that radium is and what the shielding was, if any, and whether it sat on some boat underneath someone's chair. Who knows, you know? So we don't ask questions like that. And this is a really ingenious experiment. I have to say, I really think it's cute. You line the bottom of this chamber with radium, and this is a whole bunch of plates of aluminum, very close together. And then you have an aluminum foil here, and this is now a gold leaf electroscope. I'm not sure how many people in the room have ever heard of, let alone used a gold leaf electroscope. I have to say the radioactivity course given to me by this former student of Rutherford included doing an experiment with a gold leaf electroscope. So I may be the youngest physicist alive to have actually used one. Basically, it's just a thin foil of gold here. This is some solid conductor. You charge this thing up, so now this is repelled by that because there's same charge on both. They're insulated from one another. And now this thing will stay up, in principle, indefinitely if it's in very dry air. But if you get radioactivity coming in here, it ionizes the air, and so the charge leaks off, and this thing droops back towards zero. And in fact, I remember going in looking with a sort of a microscope arrangement on the glass, on the gold, and seeing how far it had moved. Anyway, that's what he did. Pardon? Oh, bravo. And you're younger than me, so okay. So, so what it amounts to is if the alpha particles, I mean, you're going to have a certain flux of alpha particles going through here, and this thing will deflect, or this thing will droop at a given rate. You now put on a magnetic field, and it doesn't take much to deflect these alphas enough so that what would have gone through this long, narrow channel instead hits the edge. And so he simply plotted here the percent of rays deviated, that is, the percent that don't get through, as a function of the field strength. Then he connected these foils so that, well, first of all, he needed to know the sign. Was it positive or negative? So all he did was at the end of these foils, he put a little doodad here over so that if they bent this way, they would continue into this chamber more than if they bent that way. And I've seen this rig. The McGill has a museum of Rutherfordia from when he was there. This whole apparatus is about that big. So, and made out of glass. I mean, the parts that aren't metal are made out of glass. It's quite impressive. And so that way he could tell the charge. And then what he did was he removed the magnetic field and he connected the alternate plates to 600 volts. So 600 volts, 0, 600, 0, 600. And now he could observe a 7% reduction in the transmitted alpha particles. So from that he could get the E/m ratio and found that to be half of hydrogen. So that doesn't prove it's helium, but soon on, well, this is just his words in Philosophical Magazine in 1903, the succession of chemical changes taking place in radioactive bodies is due to the succession of alpha rays, i.e. the projection of a heavy charged mass from the atom. Once you know it's heavier than hydrogen, you know that you can be going from one element to another. That is, if you have their primitive understanding of what an element is. So right away, he knew they must be going from element to element. So that was the first recognition that he was transmuting elements. So the alchemist's dream of turning one into another, one element into another, he'd nailed down. And they were soon speculating that the alpha particle is nothing but a helium atom minus 2 electrons, but which would, of course, fit the E/m ratio, but they hadn't yet proved it. So he moved to Manchester. They, not unlike these days, they lured him, A, with a really good lab with lots of money and support, but B, it was at the center of the physics world of those days, or near, well, the center was really Cambridge, and so he was clearly easily lured. So he went there, and then Geiger was an assistant to the former head of the lab, and so he became Rutherford's assistant, and they devised between them this method, i.e. a Geiger counter, of counting alphas one by one. So you could tell the number of alpha particles that you'd received. So with this device, they could determine the number of alpha particles emitted from a source, And then they could, in a separate experiment, collect all of the alphas onto a conductor and measure the charge. So they've now literally got the total charge per second or whatever unit they want to use. And from the other half of the experiment, they know the number of particles per second. So divide one by the other, and you've got the charge. So now we found the charge to be 2. So if you have an E over M ratio of a half, by knowing you've got a charge of 2, you know the mass is 4. So he's getting close to putting the nail in the coffin. And then, in a marvelous experiment, I have to say I really enjoy these. In this case, he took radium emanation in this case, so it was the radon gas from radium, put it inside a glass chamber, which was inside another glass chamber where the difference, the volume between the two was evacuated. So we've got the emanation decaying here, and outside a very thin-walled glass chamber, and then outside it, a vacuum. And as the radium decayed, or the emanation decayed, the amount, and he looked at what gas content was in the vacuum by a spark, looking at the spectrum, and he could see the amount of helium increasing from 0 to some number as the decay in the other chamber was decreasing. So in other words, the alpha particles that were in the first leaked through the walls, went through the walls, decayed through the walls, and were trapped in the second chamber where they were identified as helium. So he had it completely nailed down. These things were helium. So again, when you routinely think of alpha particles, Rutherford got you there. Then we now start on the path to the nucleus, and this is the one that most of us had in school. And I think most of us kind of imagined, I did anyway, that this was kind of a shot in the dark. Rutherford just kind of tried to scatter alpha particles off a gold foil, and wow, something unusual happened, and he said, yes, this is the nucleus, and it was all over in moments. Well, first of all, you see, he had a long history of logical steps through this process. And what he had noticed, what took him to this experiment, what he had noticed was that if you had a source decaying with alpha particles, you put in some kind of collimator and then looked at it on a screen. I mean, they had these zinc sulfide screens or I think this was in fact photographic plate, so you can do it on a photographic plate. So if you have just one collimator, you get a very sharp image on the plate. If you put some gas in the way or a foil in the way, you see tails to the peak, right? We know it as alpha scattering. That was puzzling to him because, why would that happen? And so he thought it would be a good exercise for a student. Ernest Marsden was an undergraduate in a training program to play around with doing some research. And one of Geiger's jobs was to supervise students like that. So Rutherford, no doubt, said, well, why don't you just see what the scattering of alpha particles, I had this little problem from a few years ago, let's try and track it down. I mean, I think all of us who've had a student have done something like that, right? We're not as inspired as Rutherford, I guess, but there you go. So what he did was, here's a source, so there's some emanation included in this, and so the source is, of course, spewing out alphas like this. He's got an absorber here, a reflector here, a screen, a fluorescent screen, and a microscope. So if this were all to make sense, and you would only have forward scattering, then an even slightly backward scattering, you would not end up seeing anything on this screen. Now you have to understand, at the time, the model of the atom was something called a plum pudding model, but most of you have heard that. But it was thought of as a sort of cloud of positive charge with negative electrons kind of embedded in it. And this is a nice stable arrangement. And you can easily get, Thomson did all sorts of games getting stable arrangements of all the electrons in this positive charge. But if you've got a bunch of electrons and this diffuse positive charge, there's no way an alpha particle, which is positive and lots of oomph, is going to do anything but just go through and maybe make little scatterings, and that's what Rutherford thought he was looking at. But instead, almost immediately, They observed scattering. First of all, they immediately saw signals here. They found it changed with or increased with the A of the reflector, with the thickness. Even 0.6 microns of gold caused greater than 90-degree scattering, and something like 1 in 8,000 incident alpha particles scattered through greater than 90 degrees. You have to realize some poor slob is looking through this microscope and counting flashes as they occur. And I mean, if you're waiting for 1 in 8,000, you may be hanging around for quite a bit. But this was done by Geiger and Marsden at Rutherford's instructions. But this is a quote from Eve. Rutherford stated later that he was enormously impressed with the fact that when the alpha particles are fired at a very thin gold leaf, a very few return almost back towards their source, as if a bullet fired at a sheet of paper should bounce back towards the rifle. So it was as stunning as that. It was not, I mean, it was a surprise result, but it was not, it was in a logical progression of experiments that Rutherford was involved in. So nobody could figure that out. This happened in 1909, as it says here. It took him nearly 2 years for the light to come on. As you can imagine, what is going on here? And so sometime in early I've already explained this. In early 1911, he went into Geiger's office and said, I think I've got it. I think I know what's going on. And so what we might think of, especially as nuclear physicists, was a monumental event. He was uncertain enough about it or cautious enough about it that the first publication in March of 1911, now nobody can read this, I can almost not read it, but it was in the Proceedings of the Manchester Literary and Philosophical Society. Hardly phys-rev letters. So it was a cautious announcement. It said the atom consists of a central electric charge. He doesn't yet say it's positive or negative. Concentrated at a point and surrounded by a uniform spherical distribution of opposite electricity equal in amount. And it follows that the number of scattered particles per unit area varies as cosecant to the fourth of pi over 2. This law has been experimentally tested by Geiger for alpha particles and found to hold within the limits of experimental error. So this is Rutherford scattering, this is about the only thing that we remember him for in sort of by name. This, he had already worked out what the consequences of having scattering off a hard core. I might also say that the paper that was the backscattering paper was published under Marsden and Geiger's name. It was not Rutherford's name. So Rutherford wasn't one of these guys who'd sort of grab all the results for himself. Maybe also he was cautious that he didn't know how to explain it, so it was safer to have it on his assistant and his graduate student or his undergraduate student. So he gave a more complete account in May 1911 in the Philosophical Magazine. Neither publication did he say the word nucleus. So it was another 2 years till October 1913 where he said, the observations on scattering afford strong evidence for the theory that the atom consists of a positively charged nucleus of minute dimensions surrounded by a compensating distribution of negative electrons. So he had it by 1913, but what's interesting was between 1911 and 1913, one of the reasons he didn't make more out of it in 1911 is this damn model wasn't stable. I mean, if you had electrons distributed around a sort of a mush of positive charge, then that could be made stable. The electrons would orient themselves in a particular way. But now you've got a positive charge in the middle, electrons outside. Why doesn't it all go lump together, right? What's holding them out there? What's going on? You'd expect they'd radiate and so on. I mean, you probably know all these arguments. So it turned out in 1911, later part of 1911, Niels Bohr was a postdoc at his lab. He'd gone initially to Cambridge and then kind of didn't like Thomson so much, so he moved to Manchester to work with Rutherford. And Bohr, of course, scratched his head for at least a year over it, and then suddenly decided, well, if I put together the recent Planck theory, the Planck quantum, and take my length, order of magnitude of length as the circumference of the orbit, and times the mass of the electron, and make that equal to the Planck, or a multiple of the Planck constant, by golly, it all works. It's stable because I say it's stable, because it, has this Planck's constant controlling it. So it was kind of a stability by fiat, but nonetheless, it seemed to make sense. And so that's what Bohr did, was more or less give Rutherford the confidence to go with what he had come out with first from an experimental perspective. But it's worth saying the first paper by Bohr says, in order to explain the results of experiments on scattering of alpha rays by matter, Professor Rutherford has given a theory of the structure of atoms. According to this theory, the atom consists of a positively charged nucleus surrounded by a system of electrons. So it was Rutherford's model that Bohr took and made plausible. So, when we talk about the Bohr atom, we probably should talk about at least the Bohr-Rutherford atom. And I suppose when we talk about Geiger counters, we should talk about Geiger-Rutherford counters too. With that, modern atomic and nuclear physics were born. Now, he didn't stop there. I mean, that's about all we normally think of in the case of Rutherford. This, by the way, is what he looked like in 1911. That's Rutherford. That's Einstein. That's Marie Curie. And I don't know, people in the audience might know the others. I'm not sure. They're all identified somewhere, but I couldn't easily find it. Now, artificial transmutation. I mean, what he had was, up until then, what anybody had was what nature gives us. That is, natural radioactivities. So Rutherford already thought, can't we make this happen somehow by something we do? So the first thing he did was use the alpha particles from the decay of radium-C. So this is just a radium source. And he studied the effect on various gases. So in other words, here's the source. This is just a vacuum chamber into which he can let gases in by stopcock arrangement. This decays, sends beam out this way. There is a scintillator there in the famous microscope, and the poor slob back here looking into it. And so you see what happens. Whatever you see here looks like alpha particles. And of course, Rutherford was pretty good at identifying alpha particles by then, by just seeing what their scintillations looked like. So, but he found that if he put hydrogen gas, then 1 in 100,000 alpha particles, and again, that gives you an idea of the strength of the source and probably how long this guy had to look in the microscope, that it gave rise to a high-speed hydrogen atom. So he actually concluded this must have come from a head-on collision between the alpha particle and the nucleus of hydrogen. And from that, he deduced the radius of the nucleus. Pretty good. It's not far off. As I say, these guys were smart. Or this guy was smart. Now, when he put in helium and oxygen, he didn't see any hydrogen nuclei. I suppose he did it to just check that it was really the knock-on or the recoil protons. But when he put in nitrogen gas, he again saw protons. Well, he didn't call them protons. I saw hydrogen. And so his report in 1919, it's difficult to avoid the conclusion that the long-range atoms arising from collision of alpha particles with nitrogen are not nitrogen atoms, but probably atoms of hydrogen or atoms of mass 2. If this be the case, we must conclude that the nitrogen atom is disintegrated under the intense forces developed in a close collision with a swift alpha particle, and that the hydrogen atom which is liberated formed a constituent part of the nitrogen nucleus. Pretty good. That was the first indication that there were somehow hydrogen also contained within the nucleus of other atoms. So that was the first nuclear reaction ever. So this was the first time, but then he moved to Cambridge when Thomson decided to retire, so I've already explained that, and he built up a pretty powerful team there. I mean, this was after the war, and so a lot of these guys come back from the war, come back from whatever they were doing, so he got together a pretty good group of people. And then, so this is quick sort of summary through. In 1920, having recognized the special role the hydrogen nucleus plays in nuclear structure, Rutherford proposed that it needed a name of its own, and he suggested the proton. And the name stuck. So whenever we talk about protons, we can thank Rutherford not only for first identifying them, but for christening them as well. The same year, that is 1920, he suggested and this is by this time they're starting to know something about isotopes. He suggested the extraordinary possibility that there was a particle of mass 1 and no charge, that there really should be something to make everything work. And 1932, Chadwick at Cambridge, so this is one of Rutherford's younger colleagues, so it was all under Rutherford's stimulus, used the alpha particles from radium emanation, so again, a natural source of alphas, to induce the alpha N reaction on beryllium. And he used detailed balance, actually, to determine that it wasn't gamma rays coming off, but it was neutrons, so he could determine what the mass was coming off. So we have we have obviously Chadwick to thank for the neutron experiment, but he wouldn't have done it without Rutherford's encouragement and support and so on. Then finally, the sort of coup de grace here is they were doing their best to accelerate particles, with a real accelerator. So to get away from having to use natural radioactivity, but to produce their own. And so Cockcroft and Walton was an engineer, Cockcroft was a physicist, and would both be probably called accelerator physicists these days. And so they were struggling to get their generator up, and it started at a few hundred kilovolts, and they cranked it up. I suppose I should say kilovolts rather than KeV here. They reached 710 kilovolts. And like all accelerator physicists, they just wanted to keep pushing higher and higher, right? They didn't want to give it up. That nothing's changed since then, right? Rutherford told them, I think in those words, stop fooling around and bombard a lithium target with the proton beam. They did. They immediately saw alpha particles on the fluorescent screen, which Rutherford, as an expert on alpha particles, could say, yes, indeed, those are alpha particles. So they had actually done the reaction here, lithium-7 plus proton going to 2 alphas. And that, any of you who are old enough to remember the sort of popular concept of splitting the atom, this was the first splitting the atom. Those were the words that were used. This was headlines around the world. Rutherford had inaugurated accelerator-based physics, whether nuclear or particle. So, research style. He published 189 papers that I could find. 108 had one author, him. 71 had 2, 2 had 3, and 1 had 4 authors. And it's not as though Rutherford was the kind of director who grabbed all the glory. As I said already, the classic backscattering paper he left to Marsden and Geiger, so it's not as though he took his graduate students' stuff and wrote it up under his own name. This was the way science went in those days. It was maneuverable. You could go, especially with a little piece of equipment like that, you could go from idea to design to execution to the published report in a few months. And these people seem to know how to publish fast, too. You could get it to the publisher. I'm sure there were no referees, and, they had it out in no time. Interactive. Publications actually included the functions of today's email in the archive. And my favorite quotation, this is from an article that Rutherford and Wood wrote in the Philosophical Magazine in April 1916. It was the first evidence for beta delayed alpha decay, a reasonably important result. The beginning, more or less the beginning sentence, but certainly well into the introduction. There are still a number of points that require further examination, but as neither of the authors is likely to have time to continue the experiments in the near future, it has been thought desirable to give a brief account of the preliminary results. Imagine you say that in your introduction to a phys rev letter. But that meant this could get out there. I mean, if he'd waited until, he'd nailed it down and had time to do all this stuff, it might have been 10 years later. It might never have come out. Resources mattered. That hasn't changed. Well-equipped lab and good support attracted Rutherford actually to McGill in the first place, but was certainly part of the lure to Manchester and Cambridge. No health and safety concerns. It really is true. To see if radioactivity changed at high temperature or pressure. People wondered, is it affected by temperature and pressure? And so this was back in 1903 or 4, something like that. So what did he do? He placed radium together with cordite, that's an explosive, and he put it inside a steel bomb and blew up the cordite while measuring the gamma rays outside the 2-inch thick walls. So in other words, this was thick enough so that it didn't blow up. I mean, it didn't shatter. Although, imagine your DOE officer is presented with this and you say, oh, it won't shatter, But this is probably a huge amount of radium and a lovely explosion going on inside it. And of course, what he did was measure the activity before and measure the activity after, and they were about the same, within 5 or 10%, which was good enough, and so concluded that radioactivity wasn't affected by temperature and pressure, because obviously it generated quite a lot of pressure, not to mention temperature. Dependent on models, that's an intriguing one that I hadn't realized. In those days, the whole idea of using a model to think about science was controversial. British physicists made models, I think from Faraday's on, their minds were on models. But Europeans, the Germans and the French, thought that such visualization was arbitrary and rather childish. You make some model, how can you know that your conclusions from that model are going to follow? So it was controversial, and there's an exchange here that I really enjoy. This is a German chemist, wrote in 1895, to set realities, demonstrable and measurable magnitudes, in definite relations with one another, so that when one is given, the others will follow. That is the purpose of science. And it cannot be fulfilled by the substitution of any hypothetical figure. So you just learn the rules. You do this, that comes out. Don't mess around with some crazy model. Now, I love the reply, which is, I hope the Germans in the crowd will understand, doing without images might be all right for a German who plods by instinct, but a Briton wants emotion in his science, something to raise enthusiasm, something with human interest. And of course, the best part of it is it's by an Irish physicist. It was that kind of debate going on at the time, and I think we can agree that Rutherford's nuclear atom and its elaboration by Bohr settled the argument once and for all in favor of models. And we all think in terms of models these days, and I'm sure it's not just Rutherford and Bohr that we can thank for that, but it is a kind of turning point in science where it went from rules to a kind of modeling approach. So his influence launched subatomic physics. I mean, in a sense, almost everything we do in nuclear and particle physics has been influenced by Rutherford's discoveries and methods. He established our approach, first to bombard a target with an ion beam, at first a natural beam, and then an accelerated one. Most particle physicists and nuclear physicists, or at least many, depend on an accelerator, and we do the same thing. We put a thin target in and have a beam going. I mean, there are fancier beams, higher energy, and so on, but the methods were first invented, if you want, by Rutherford. He inaugurated our vocabulary. This is probably only a partial list, but nucleus came from him, proton. The neutron is probably Chadwick, but, Chadwick was working with Rutherford, so who actually thought of the name is another question, but he was certainly part of discovering the neutron, as well as alpha and beta particles. And he first recognized and wrote down the exponential growth and decay law. Now, that's just a partial list, but these are things we still use and depend on. He affected our way of thinking. So, although he wasn't the first to devise a model for some unseeable phenomenon, the success of his atomic model established the value of his way of thinking and set the pattern we still follow. And another interesting one that I wouldn't have thought of, he popularized the field. I say here he was a larger-than-life character. He was he was large. He was a big man. He apparently had a very loud voice, and he was very good he was a good interview subject. And so, when he split the atom, he was a good guy for the newspapers at the time to come to get their news. So he made headlines around the world. I'm not going to give the epilogue because I'm near enough the end. I had a little thing that tied to work of modern times. But let me just quickly go to the very last picture. There. That's a picture of Bohr, who is here, and Rutherford at some kind of picnic in the 1920s. So you get an idea of the looks of these people. So that's it. I hope I've impressed you with what Rutherford has done. Yeah.
I have a comment about fame in science. Pardon all the name dropping, but 25 years ago, I was having lunch with Chandrasekhar at the University of Chicago Faculty Club, and I asked him if he was pleased that there were a couple things named after him. And he said, well, yeah, I suppose it's okay, but 50 or 100 years down the line, nobody's going to call these things after me. They'll just be absorbed in the field. They'll be the white dwarf mass limit, for example.
Mm-hmm.
He said, for example, who calls it the Rutherford model of the atom anymore? Science becomes anonymous. And so I mentioned this anecdote one time out at the Mitchell Ranch when Stephen Hawking and the string theorists were out there. And Stephen Hawking heard this, and finally he spoke up to comment, or should I say his computer did. And he said, they will always call it the Dirac equation, and I hope they always call it Hawking radiation.
In preparing for this, I actually read an article which looked at the citation record for Rutherford. And the conclusion of it was that if you invented the field and sort of almost everything is due to you, you don't get many citations because, who's going to say, when you use the model of the nucleus or the atom with the nucleus, are you going to quote Rutherford? Just as I suppose people who write papers on relativity don't give massive citations to Einstein. So, yeah, sometimes you can be too famous and too successful, I guess. Yeah.
Was his health affected by his work?
Actually, no. No, what he died of, in fact, he was 67 or something when he died. He was actually climbed up a ladder in his home to fix something. No, 60. It was in 37 and he was born in 71. So he fell from a ladder and injured himself here, and he died of a strangled hernia, meaning that if they'd taken him to the hospital and so on, he could have had it dealt with. But he was a strong and tough guy, and so with a little pain, it'll go away, and it did go away, but so did he. A flax is a grain, right? So and I gather that these flax farms, you didn't actually plant the flax, but you went and collected the natural flax that grew in the swampy area of New Zealand. So I don't think he actually went around planting. He went around picking up. And in fact, the father built a flax mill. And so I think later on in his life, he was not so badly off. I mean, not so poor, but with 12 kids, I mean, God, you have to, professor's salary, but he'd still be poor with 12 kids. Yeah.
When you talk about the discovery of the alpha particle, what was the state of knowledge about helium? Was it known?
Helium was first identified. Well, apparently its existence was first deduced in 1850 or something from looking at stars of some kind. I mean, the astrophysicists may know that. But it was Ramsay who actually chemically isolated it for the first time in 1895, a year after he isolated argon, 1894. And those were the first rare gases. So Rutherford's experiments with the alpha particle and his identifying it as helium were done within the first decade after helium was discovered.
And the mass of helium was not known.
Well, you sort of deduced it, right? But yes, they could measure masses, but in crude ways. But that, as I said, there were these puzzles like the potassium and argon inversion, and so they had very round numbers. So, I mean, I'm not sure if they knew that the helium mass was 4.00 or just about 4, but they did know that, yeah. Yeah?
Why is proton named proton? What's the origin?
You have to ask Rutherford. I don't know. Positive, and I have no idea. I don't think he gives an explanation. He just says it deserves a name. Let's try proton. And then I guess neutron follows naturally from that. But, yeah. Yeah, well, it could be something like that. Could be. Could be. That's a good point. So the answer is I don't know. Does anyone else know? Okay. First. Okay, thanks. Yeah?
Rutherford was a member of the Royal Society.
Mm.
Therefore, anything he sent for publication was not refereed.
I don't think any papers were refereed.
If you need to publish in that journal, you have to find a member of the Royal Society.
To submit it.
That's why Flashman published the paper on the...
Yeah. But I don't think anybody ever got refereed until later on. I mean, there's a famous story about Einstein submitting a paper to PhysRev, and the editor sent it to a referee who sent back comments which were actually negative and actually right, as it turns out. I mean, Einstein had made a mistake. But Einstein was so offended that his paper would be refereed at all that he never again submitted a paper to PhysRev. He submitted it to journals where it would be accepted unrefereed. Yes.
You didn't say it, but I assume that the neutron conjecture was based on Harry Moseley's.
I think that, and I mean, after all, it was Soddy who got the Nobel Prize for identifying isotopes. So it seems to me, surely it follows from the fact, I mean, once you think of isotopes, what makes it one different from another? Well, surely it's the addition of some neutral particle. So I'm not,
With the mass of, assuming that it has a mass close to 1, must come from comparing the atomic numbers to the mass.
perhaps, but also Rutherford was remarkably intuitive, as I hope I made it clear. So sometimes, these guys, it was almost like magic, right? That they, with an infinite number of wrong choices, they managed to find the right one. Of course, I guess all the other scientists who managed to get the wrong one we've never heard of, so Actually, yes. That was my penalty for giving the talk at this conference in Canada. They asked me to write it up for Physics in Canada. So yes, there is an article that I've written. It hasn't quite been published yet, but it's in the process. Being refereed, yeah. Actually, there is a story there, and I won't go into it in detail, but it was sent out to be refereed by a gentleman in New Zealand who is also a physicist, not a nuclear physicist, and is a passionate Rutherford person, and has written a book on Rutherford which is self-published, which gives you perhaps an idea that it's not fantastic. And he wrote me, there were 27 comments, individual comments and criticism of what I wrote, and 25 of them were of the sort where at the beginning I said it took him almost 2 years to figure out what, what the backscattering meant. And he said, no, it was 20 months, so you should say more than 1 year instead of nearly 2. And they were all of that sort. So if you have trouble with physics referees, I hate to think what history referees are like. So I kept it at nearly 2 years, I have to say.
You mentioned this nice little museum that they have.
Yes.
So I've seen it. It's actually, if you go up there, give a colloquium.
Yeah, it's actually wonderful. I mean, it's 2 rooms with a physics professor who is the custodian and who will bend your ear for hours and hours if you let him describing each piece of equipment. So, yeah, no, it's great.
Okay, so let's thank John once more.